Hello Energy 301 students, it's Dr. John Shruggy. Welcome back. We're continuing our first module in the course that's just sort of an overview of the physics of the atmosphere and so on, just giving us some vocabulary and so on that we're going to be using in problems and so on throughout the rest of the semester. And today we're just talking about pressure. This is again not the most complex lecture you've ever seen. We're just making sure we're all up to the same speed as to what we mean about pressure and so on. You know, you're all survivors of physics classes and stuff like that to have gotten to this point in your education. And so I know that you know about things like pressure. You can kind of picture all the little air molecules moving around, and as they hit the insides of a container or something like that, they're exerting pressure on the sides of the container. But it can be hard to picture what that means in the atmosphere. There's a better way to picture pressure in the atmosphere. You know, the atmosphere is made of matter, and therefore it has mass. And it exists in the gravity field of the Earth, and anytime you have mass in a gravity field, the object has weight, even if that object is air. I mean, air has mass, and gravity pulls it down towards the center of the Earth. A good interpretation of what we mean by pressure in the Earth's atmosphere is that pressure is the weight of the air above you. And this is actually a really useful interpretation for lots of reasons in atmospheric sciences, and atmospheric scientists really like to think of pressure in this way. It leads to lots of useful ideas. You know, you could picture like a unit area on the surface, and then if you picture all the air from that location up to the top of the Earth's atmosphere, you could add up all that weight and you would get the pressure that that air is exerting on the surface there. And you could even use units of weight to help you with that. I mean, for example, a good unit of pressure is pounds per square inch, and as it happens, it works out to be 15 pounds per square inch is roughly the pressure at the surface of the Earth. I mean, that's amazing if you think about it. I mean, a square inch is not very big, and 15 pounds is a lot of weight. This is a useful way to think about pressure, like, you know, as this column of air that's pushing down on a given location, in part because it helps us understand an important property about pressure, namely that pressure always decreases with respect to height. That would be hard to figure out why that should be if you're just thinking about pressure the way you learned about it in a physics class or something like that, is like, you know, the force exerted by all these little molecules and so on. So, I mean, you can see why pressure would have to decrease with respect to height, as the object, as your instrument that was measuring the pressure got higher and higher in the atmosphere. Well, there can only be less air above you than there was when it was down low, right? I mean, you have passed some of the air along the way. Therefore, the pressure can only be less the higher up you go in the Earth's atmosphere. That's a useful thing that has lots of applications in atmospheric sciences, but we have to get rid of this unit of pounds per square inch. I mean, 15 pounds per square inch, that is not, doesn't sound very scientific. It doesn't sound the way that the meteorologists talk about pressure. Meteorologists tend to talk about pressure in units called millibars. That's abbreviated MB. And at the surface of the Earth, there's about 1,013.25 millibars of pressure. Ballpark figure, think about 1,000 or something like that. We'll talk more about what pressure means in just a little bit, but to tie it to the Energy 301 class, I want to make sure you understand pressure doesn't directly affect either electrical load or yield. It isn't like the efficiency of a wind turbine depends on the pressure of the air around it, or the efficiency of some solar cells or something like that will be affected by the pressure or something like that. It's not so much that the pressure directly affects the electrical load, yield, or the electrical load, so much as in patterns of pressure are going to create winds, and that will directly affect both electrical load and electrical yield. And to understand why, you need to understand how pressure can be used to set up one of the key forces at work in the Earth's atmosphere, the so-called pressure gradient force. This is just one of about 5 forces that create the winds, but it's a key force, and it is a force that pushes air from areas of high pressure towards areas of low pressure. This is how a spray paint can works. A spray paint can has relatively high pressure inside the can, there's lower pressure outside of it. When you open up the valve on the can, the gases inside the can go from higher pressure towards lower pressure. They are accelerated in that manner using the pressure gradient force. And in the same way, there's a force acting on the air at any given time, pushing the air from areas of higher pressure towards areas of lower pressure. It doesn't mean that the air is necessarily going to flow from higher pressure towards lower pressure, because there will be other forces at work. Just like any given object, you know, to understand how the objects will be accelerating, you need to understand the composite of all the forces that are at work on that rocket or that potato or whatever it is that you've got in motion. and the air is no different, you're going to need to know that all these different forces that are acting on the air parcel to create wind, but we don't necessarily, right now we're just thinking about it in context of pressure. Now, if you think about this problem, I'm just showing you a slide that you've already seen once before, where we said, if you think about pressure as just as the weight of the air above you, therefore pressure should always decrease with respect to height. Well, let's think about what that means for the air pressure at different weather stations, say, on a mountain. If I just have a mountain here and I put 3 weather stations on it, weather station 1, weather station 2, and weather station 3, you would ask how are they related? Well, okay, if you know that pressure always decreases with respect to height, you can already pretty much confidently say that the pressure at station 1 will always be greater than the pressure at station 2, which will always be greater than the pressure at station 3, which, if you think about it, is kind of weird. I mean, yes, they're all at different altitudes, but there seems like there should be some way to correct for that. I mean, what we really mean is what's the large scale on a weather map type pressure of this location. We should be able to somehow remove the effect of the different changes in heights here. And there is, in fact, there is a way we can do that. The quantity that we're going to be using is called mean sea level pressure. Mean sea level pressure is a number that corrects the observed pressure, which was taken at a height of a station that is not necessarily at sea level, and corrects it as if that location were at sea level. There's actually a number of different ways you can do this. But then this way, the pressure observations that you are taking reflect the large-scale patterns, not just how high you are above sea level. I mean, if we just were using measures of mean sea level, measure just the station pressure, what we actually observe, well, then a station that is high above sea level, like Denver, would always have a low pressure system over it. But that's not true. There can be relatively high and relatively low pressures over a location like Denver. Because it's high above sea level doesn't necessarily mean that its pressure is always high or always low for it. Okay, yeah, the pressure at Denver is always lower than the pressure at Omaha, but we want to have that corrected. Can we correct the pressure for how high it is above sea level? Now, the actual math of how to do that is actually pretty complex, but if you correct the pressure observations with respect to their altitude, then 3 stations that are close to each other, like Station 1, Station 2, and Station 3, are all going to end up with approximately the same mean sea level pressure. We have corrected the pressure by adjusting it as if that station were actually at sea level. Now, ideally, a great instrument for measuring pressure would be the barometer. I like that word, barometer. Baro is a prefix that means something like weight, and meter means something like measure. And so it's a machine that measures the weight of the atmosphere. Barometers are instruments that have kind of like a dish of a liquid, and then there's an upside down tube in there, closed off at the top, a little vacuum at the top, and the pressure of the air around the liquid pushes the liquid up that tube. And how high the pressure is will influence how high up the tube that liquid will go. Now, in practice, we like to use mercury for that liquid because liquid mercury is very dense. If you use something like liquid water, which is much less dense than liquid mercury, that tube would have to be about 35 feet tall. Not a very easy weather instrument to work with. And frankly, even with a liquid as dense as mercury, it's still a very delicate and fragile instrument. Typical sea level pressure on the Earth is about 30 inches of mercury. So that glass tube there is about 30 inches tall, holding mercury, a dangerous liquid metal. Mercury barometers exist. They are kind of the gold standard of how you measure pressure. I have a picture of one on this slide here, but that doesn't mean that it's necessarily a very easy thing to work with or whatever, and you certainly can't use them in certain kind of applications, like, for example, on a weather balloon, where the instrument would be floating away. I mean, how are you going to have a 30-some inch glass tube full of deadly liquid mercury floating away on a balloon? There's all kinds of problems there, right? So more commonly in atmospheric sciences, a more practical way to measure pressure is with an instrument called the aneroid barometer. Aneroid is a fancy word that means something like dry or without a fluid in it. And I attached a little schematic here to how an aneroid barometer works, but it basically has like a little canister, kind of looks a little bit like a tuna can in there, and it's partially evacuated. It's a partial vacuum inside of it, and the pressure of the air around it can crush that little can a little bit, or if the pressure is lower around it, the little can can stretch back out. And then there's a series of levers and hinges and stuff that connect that canister to just a needle operation there. And so as the pressure changes and that little canister expands or contracts, it can move a needle from side to side and give you a good approximation to the air pressure. It's an easier instrument to calibrate, it doesn't involve deadly liquid metals, it's actually a pretty straightforward piece of equipment to work with, and they can make them, like the size of a dime. I mean, you could put a very small, very light one of these on, say, a weather balloon, which can't lift some big heavy thing full of liquid mercury or whatever. And we can, get the balloon, we can get measurements of pressure then any place in the atmosphere. So just to kind of review here real quick, pressure itself doesn't directly influence electrical load or yield, but changes in patterns of the pressure are going to cause winds and cyclones and anticyclones that will have very direct impacts on both electrical load and yield. So if wind is where we need to be going with this, let's go there. Our next lecture will be about winds in the atmosphere and the basic physics of winds.